In this video, I'm going to teach you about mechanical energy. So as you learned in previous videos, work transfers mechanical energy to and from a system. Now this word, which was in the previous video, is used all the time in everyday life. Now in physics, if you look up the definition for energy, it will tell you it's the ability to do work. And that means very little to me. So my goal in this video is to help you conceptualize this term energy through examples and also through calculations. Mechanical energy has two different types: kinetic energy and potential energy. Kinetic energy is the energy of motion. So this could be me running. It could be you driving in your vehicle. It could be an apple falling from a tree. It could be atoms oscillating and colliding. Potential energy, on the other hand, is dealing with energy that is stored in an object's position. So this could be me holding a bocce ball above the ground. It could be energy stored inside of your body. Inside of glucose is stored energy that has the potential to do work. Let's go ahead and now look at your College Board equation sheet, and let's start with kinetic energy, which has the formula 1/2 the mass multiplied by the velocity squared. Kinetic energy has a unit of joule. A joule is a derived unit. It's the same unit I spoke about in the previous video dealing with work, which means the base SI units for a joule would be a Newton meter. So let's look at the units for calculating kinetic energy here. We have mass, kilograms, multiplied by velocity squared. Well, velocity would be meters per second, but it's squared. So we get meters squared over seconds squared. And I'm telling you that this is a joule. Let's look at it. So a Newton, as you know, is mass multiplied by the acceleration, units, meters per second, per second. So if I take the fact that that is a Newton, and I now multiply it by a meter, I get a Newton meter, which is a joule. Okay, so I'm going to do this with all of our energy formulas to make sure you see, you know how important that is to me, that you understand how these units work. Now, another point I want to make is kinetic energy is always positive. Here's why. Look at mass. Mass is a positive number. Look at velocity, which, yes, is a vector, but guess what? It's squared. So that means it will become positive. So kinetic energy, therefore, is always positive. So here we have an object. It's on a surface without friction, and a force accelerates this object a distance d. So work was done onto this object, and that resulted in an increase in energy because the block went from a state of where it was not moving to where it was moving. And if it was moving, it has kinetic energy. All right, so now let's go ahead and look at potential energy. Hey, Stickman, good to see you again. Let's look at an object's position, and the Stickman's going to show us this. So Stickman here is holding an object. And as you can see highlighted on your screen here, we have the equation for potential energy. This is the gravitational potential energy. So there are two types we'll talk about in this course. The first one is gravitational potential energy, which can be represented with a capital U subscript G, also capital PE subscript G, and those are equal to mass times little g multiplied by the change in height. So on the College Board sheet, you can see delta y here, And that is here represented just as that height, the change in height that occurs. So I wanted you to get a look at that and the differences between them, because I'm going to I will put both of these, I use them interchangeably. I want my students to be aware of both. So there you go. Now, mass, gravity, height. Let's look at the units. Again, mass, kilograms, acceleration due to gravity, meters per second, and then we have height in meters. So, once again, you will get a joule. All right? Now, when we're dealing with gravitational potential energy, we set something called a zero line. Okay, and at that zero line, the gravitational potential energy is equal to 0 joules. All right, but students struggle with this because it's arbitrary. You get to choose where to put this line. And so by working out examples in class, you're going to understand that you have to choose wisely where you put the line to make life easier, to make calculations simpler. So let's say I choose to put the zero line here where Stickman is holding the object. Then that means at that height, there is 0 gravitational potential energy. Now, if Stickman then drops the object below the zero line, that means the gravitational potential energy is less than 0. So here it's 0, but beneath that line, it's less than 0. Now, the reason why is your change in height is now going to be negative. Okay? So you have a negative number minus 0. That's going to give you a negative number, which is going to give you a negative value for the gravitational potential energy with respect to the zero line that you defined. All right. Now, what if we put the zero line down here at Stickman's feet? Well, that makes sense too. If we put the zero line there, then this object where it's currently at its given height now has a positive potential energy. Okay? Because we have now moved our zero line down to the ground, which makes sense. And with reference to that object's position, it is above the zero line. Okay? That's how this works. So you choose where to put that zero line. And again, it's best exemplified through calculations. So now let's go ahead and look at your final equation in this video dealing with mechanical energy, specifically the second potential energy, which is the elastic or spring potential energy. You can see the formula highlighted on the screen. You can see the formula highlighted on the screen. Let's look at this. So we have that the spring elastic potential energy, which is also referred to as the elastic potential energy, which could also be written as potential energy subscript E for the elastic potential energy. I want you to know all of those. I will use them interchangeably, is equal to 1/2 kx squared. Let's go ahead and look at that. K is called the spring constant. It is a property of the spring. It is a property of the material. X refers to the position of the spring. So we are looking at the change in position for the spring. How far was the object, say a spring, stretched or compressed? How far was the rubber band stretched? Those all are examples of mechanical energy and specifically elastic potential energy. Let's look at our units again to make sure we're dealing with a joule. You can see our units for K would be newtons per meter, and then times meters squared. Well, if you look at that, this one's pretty easy to see. Cross that out here and cross one of these out there. And what are you left with? you're left with a Newton meter. You could also expand this out where you have the base SI units for a Newton divided by a meter multiplied by meters squared. And again, you get a joule. All right, Stickman is back, except this time he has a bow and arrow. And in that bow, there can be stored potential energy in the form of elastic potential energy when it is stretched from its relaxed state. And that can be calculated by measuring the distance it is stretched from its relaxed state. Now, I also want to again mention, you guys, that objects can have stored elastic potential energy when they're compressed as well. Okay, so think about that a little bit. Compression or extension. In both cases, we have a change in the position of the material, the spring. So in this video, I've introduced you to mechanical energy. We've talked about kinetic energy and two types of potential energy, both gravitational potential energy and elastic potential energy. And I'll see you guys in class.